Hi, my name is Denis. I'm a performance engineer at Meta. So first of all, there's the slides. It's tinyurl.com/dystr2025. So tinyurl.com/dystr2025. Okay? Now, perfect. Now, if you're looking at your phone, I'm just assuming you're looking at the slides and you're just super interested there. I'm very sorry, there are no benchmarks for std function. I did not know this was a requirement, otherwise I would have prepared. What are we going to talk about instead? So we're going to talk about finding a string, a substring in a string. Just to be clear, we're going to be talking about n times m algorithms. There are no tables, no clever tricks, just an n times m algorithm. We're going to start with just an interview problem. Right, so how do you assume people write that during the interview? And we'll have a look at performance of those solutions. Then we'll look at what C++ standard provides us. And finally, we are going to talk about SIMD. Raise your hand if you've ever written any SIMD. Well, like, not bad, not bad. It's not a requirement, I'm just curious. Okay, so raise your hand if you think you know everything I'm going to say. Okay, that's good, that's good. Some people do, you'll be surprised. Okay, so interview problem. Like, assuming you were the interviewer and say you were given a substring in a string because you really want people to cheat on your interviews, how would you expect them to write? Just yell out, like what you would expect them to kind of produce. Like, I don't mean the complete code, but just an idea. How to find some, yeah? memcmp plus
like finding a substring in an array, for instance, could be done like with a memcmp, maybe.
memcmp, so you can memcmp from which character, right?
Yeah.
Okay. Any other options? Well, okay. I would expect them to write one of two things, right? I would either expect two nested loops, right? We check the first character and then, we check. Or we go find plus equal, so that's a sort of memcmp, but we just, the equal is memcmp, you first call find. Right, so one of two possible solutions. Assuming I was writing them, I'd be writing something like this. Can you see somewhat code? Okay, so on the left is find and equal. I don't mean for you to understand the whole thing, but you see there's a find, there's an equal in a loop. On the right, there's an outer loop, and then there's an inner loop that I call inside the lambda, right? I just moved the inner loop into a lambda because it's easier for me to read. Okay, looking at this code, do you have any performance ideas about this? What do you think about performance of this code? Is it like the same? Is something faster when?
I would say the right one is like would be faster because maybe the standard library has some overhead that the right one does not have.
That's a really good point. Please don't run to people. I will repeat, otherwise it will be taken forever. The overhead, at the very least, find and equal has to check for an empty range, right? There is a check, is this range empty? On the right, when we do two loops, we end up in a situation where we don't have to have that check. We just check for empty strings once. On the other hand, maybe standard library does something clever. And in fact, it does. So what it does is, this is a find plus equal. And if we have a look here, the find actually becomes a call to a C function memchr. And the equal becomes called to bcmp, which is like memcmp, like think memcmp. So if the C standard library is faster, and it is faster than your standard loop, right? This might have an advantage. So here is my expectation of performance looking at the two cases. Right? So one case, the first char of a string that we're looking for is rare. If it is rare, then effectively our function boils down to calling memchr, and the C standard library would just beat our code. Right? The way I'm going to benchmark it is I'm going to search for a string 22 in a bunch of ones. So there is never going to be the first character ever, and just we're going to be memchring to the end. The second case is the first char is common. So whatever overheads we have from calling those functions will be really present. The way I'm going to test it is I'm going to search for 12 in a bunch of ones. So every character is the first character. We're constantly encountering the overhead. There is also a third consideration, which is having very long needles. Like, so what if you're searching for really, really long needle, and just the comparison against the needle becomes a problem. This is so rare that I didn't even bother to check, but I'm just mentioning it. Okay. This is the difference. On the left, if you can see it, is calling find followed by an equal for the case where the first char is never encountered. And it is more than 40 times faster than our two loops. 40 times sounds pretty nice. So this is the second case, where the first char is common. And the difference here is that find plus equal is, I believe, about 5 times slower than two loops. So neither of this is good. Like, neither calling find plus equal is an acceptable implementation, nor doing two loops is really an acceptable implementation. The performance loss is just bunkers. I mean, it's acceptable for an interview, right? We don't want people to write really complicated things, but for production, no. So let's have a look at the standard library. Which ways do you know how to find a substring in a string in a standard C++ library? Yell. Sure. There's a method on the string called contains. I found the method on the string called find that returns me a position. Contains just returns a bool. Anything else? STD search. Like you have prepared. Thank you very much. Yes, there is a standard library. Ranges have search, that kind of stuff. Anything else? How about libc? In libc, str, exactly. There's str. I also added regex and Boyer, Moore, Knut Morris Pratt, those kind of searchers. They come in C++ 17, I think. I don't care about them, but I just add them for completeness. Let's look at some numbers. So let's start from the biggest to the smallest ones. This is my two loops implementation. This is a case where the first character is never encountered. My two loops implementation versus std search. Std search is just better. Turns out that std search is just better than my two loops implementation everywhere. So let's remove. It's also like two loops implementation, just better. So let's use that as our baseline from now on. Okay. The next one is str, which is about 7 times faster than search, standard search. And it is about 3 times slower than our find plus equal and string view find. So string view find, turns out, is just implemented as memchr followed by memcmp. So it's exactly the same code as what we did. This is why my code is only slightly slower. I don't know why, but anyways. So, okay, kind of looks reasonable. In this overhead for 3 times is of course a lot, but maybe if it's not so bad for the other case, maybe str is acceptable. And in fact, this is str for the other case. So when we search for 12, right? Let me talk about, so this is 30 nanoseconds when we search for 12. So the first character is common. And this is still 30 nanoseconds. So str did not lose any performance. But let's look at the other ones first. So string view find and search find equal awful, as we discussed. Then we have, well, my two loops is not very equal. So then this std search that is about 7 times better. Search find equals simple find. Right, and then str is again about, I don't know, 12 times faster, something like that. I'll be like a little bit, like going forward a little bit. So this is actually not the worst case for str. What str is doing, it checks first 2 characters instead of checking the first 1 character. So this happens to be not the worst case for str. I will show you a benchmark for the worst case, which is first 2 characters much later. But it's not going to be nearly as bad as string view find or anything like that. So what our goal becomes for the rest of the talk is to try to kind of match with the performance of str. Okay. Do you have any questions so far? Then let us talk about SIMD. It's okay if you don't know even what the word SIMD stands for. I'll explain. But let's see the plan first. So substring search is quite a lot to take like from the beginning. So we're going to start simpler. We're going to start from memcmp. Then we're going to look at memchr. And only then we're going to do search. All right. Let's write std memcmp. So std memcmp, if you don't remember, it takes 2 blobs of memory, equal lengths, returns negative number, 0, or positive number, depending on less, equal, or greater lexicographically. If you didn't have a memcmp, which C++ standard algorithms could you use to implement memcmp? There is mismatch. There is a mismatch, yes. Okay, mismatch is one. There is more. There's another one. Well, okay, so you can use in ranges, you can use find and call a zip as well. So you can zip to ranges and find. But actually in C++20, there is an algorithm called lexicographical compare freeway. That is just actually an implementation of mismatch. It's for spaceship support. That's its only purpose. But mismatch is the main algorithm. So if you open CPP reference, you will see some code like that. So if you just call the code from CPP reference, it just goes byte by byte and compares 2 arrays. In the standard C++ that you know, no fancy instructions, no nothing, can you do better than this? Just then going and comparing byte by byte. Sorry, I have troubles hearing you.
I could use a bit XORing, maybe.
XORing?
Or
I don't think so. You just compare for equal. I don't think XORing will help you much. There's a chance my microphone is falling. I'm hoping that's not true. Thank you very much. You can use big and integers. Like let's use in64s, right? And so if we're using 64s, we're in a bit of a trouble. Because, you know, for example, our pointers will not be aligned to 64. Yeah, it's definitely falling. To 64 for bits. Well, we also may have ranges that lengths that's not divisible by 8 bytes, right? Well, the first one is very easy to solve. You can use unaligned loads in C++. So while there is a requirement, you can just write this code. So you just call memcpi on a pointer, and you just copy whatever 8 bytes. And that will do an unaligned load for you. So that's one is easy. Let's deal with the other one. How do we handle the ending of an array? Let's start here. How do we compare 16 bytes? It's not a trick question. To 2 in 64s. There you go. Now there's a trick question. How do we compare 15 bytes? can you say it again? Yes, thank you. Like you are like very rarely people get it. Did you see it before? So what we can do, really cool. I had not guessed it. I saw it, people also do it, right? So what you can do is you can overlap the registers. Like it doesn't matter. You'll compare one byte twice. Okay, no worries. It works. Okay. It works all the way up to 7 bytes, in which case you have to use smaller registers just because you cannot load 8 bytes anymore. If this looks a little bit esoteric, it's not. For example, I saw this code directly in memcpy implementation. All right. Let's look at the numbers. So this is whatever nonsense I wrote within 64s, and this is a mismatch I copied from the CPP reference. And the difference is 8 times. So the compiler didn't do it for us. Can anybody guess why? There are 2 reasons, none of them really good. Well, so the comment was maybe architecture doesn't support in64. Well, compiler will like knows your architecture. At least integers should be supported, so it could use 4 bytes. I'll give you 2 reasons. One is that when you write a loop, for you it is like, oh, okay, go through the array and compare them. But what the compiler sees, it sees 2 breakpoints. It sees we reached the end of the array, or we found a mismatch. It never knows that the end of the array is actually reachable. Makes sense, right? We know, compiler doesn't. So for the compiler, this looks very similar to something like strnlen, right? The function that has a limit, but not guaranteed to be able to reach it. Unfortunately for the compiler, strnlen can be also improved in a very similar manner, because the reachability is not necessarily a requirement. We're not going to talk about it. So the second reason is not just implemented, right? This is std mismatch. So std mismatch for default operators is another 2x faster. And finally, this is memcmp, which is another 2x faster. All right. So I will explain this difference later, but the main difference is here, and this is 32 times. std memcmp is faster than whatever I copied from Stack Overflow by a factor of 32. But actually, fundamentally, they didn't do anything very much differently compared to what we did with in64s, except they didn't use in64s. In64s are integers. They're not designed to be really large registers containing a lot of different elements. They're registers that are, and they're called SIMD registers. Single instruction, multiple data. The same way we did it. Like we took one instruction to compare 2 in64s, but we actually compared 8 bytes at a time. Same idea, just bigger registers. So one note, this std mismatch improvement is very recent. This was merged into libc++ like last year, but Nicholas Clauser. Before that, when I showed this benchmark, the awful example on the right was std mismatch. Okay. So how are we going to use SIMD? We're going to use Eve library. Eve library is on GitHub. It's maintained by Joël Falcou, Jean-Thierry Lapreste, Alexis On, and me. But I'm not really interested in the library in this talk. If you want to learn about the libraries, there's, for example, this talk called SIMD in C++20, Eve of a New Era. What we're talking about is algorithms. And in Eve, it's a ranges library. There are some algorithms, and one of the algorithms is mismatch, which is what we discussed, should be able to implement memcmp. So let's see how that performs. So this is the same benchmark. I removed this completely scalar case because it's really large. But everything else, we can see that if mismatch is somewhere between std mismatch and standard memcmp. But this is slightly more than 10%. I'm really upset about it, but I'm not gonna fix it. But at the very least, you can hopefully see that I know what I'm talking about, right? This is an apple. As you can see, STD mismatch on apple is really bad. That's because the optimization by Nicholas is not yet made it there, right? Well, when I measured it. And we can also see that if mismatch is better than STD memcmp here, which makes me really proud. Okay. I say, like, you know, on my machines, this is 32 times faster, right? On Apple, there's different performance. The thing is that those SIMD instructions, they're not just part of your native architecture. Like, they come, the new generation of processors comes out and has more newer capabilities. So this is extensions to the architecture. You need to know which one you're targeting. Like, for example, when I show you benchmarks for Intel, I show you this family of extensions. It's 15 years old. So it's like your old computer should have it. When I show you Apple, this is this SIMD. It's on all your phones for sure. Like Android is requiring it. Pretty sure. Okay. I'm not going to talk more about this. The only thing I'll mention is that compiling correctly is important. This is the same mismatch algorithm with if compiled correctly versus with just O3. So with March native versus O3, and the difference is 2x. Huh? Any questions so far? Anybody awake? Yeah?
Hi, my name's Luca. I'm non-technical, so as a user, I'm wondering if when you're using these libraries and that function mismatch, when you need to compile for a different architecture type, you need to write twice the code so that you have, for example, one running for Windows x64 and stuff, and then the other one for chips. So you do you write the code twice, or do you have like a function that handles that?
So a runtime dispatch based on so okay. Whenever you do ARM versus x86, you will still have the binary compile twice. So the function is written once but compiled twice, right? You're correct. What then happens is you have the same extensions for Intel. And sometimes what people do is they take the same function, compile it multiple times into the same binary, and then because, you know, oh, I have this old computer and I will run the old version of the function. I have this new computer, I will run this newer version of the function. Really complicated topic. I'm not going to go into it more than that. So that can happen. That's not what this is doing. This assumes that you just compiled your whole application once correctly. Like, I think CVision would have just one target that they compile specifically for. Same, for example, for me. All right. Any other questions so far? Okay, let's move on then. So what's inside mismatch? Assuming I convinced you that mismatch is kind of correct. Well, actually, in Eve, we just call find if plus zip, because it's a ranges library. So the whole mismatch is like 3 lines of code. A bit more than that, okay. This is cool and took us a lot of time, but absolutely not interesting for this crowd. So let's look at find if instead. I remind you, find if in a C library that's called memchr. So we're switching kind of to the second function. So this is I took a hypothetical find and ripped out a bit in the middle. That's just going to check one blob of bytes, one SIMD register of bytes. Right. So let's have a look. Here I have a pointer where I'm checking and the needle I'm trying to find. First things first, I need a type for my SIMD register. In if, this is called wide. So I declare this if wide, and for my computers, it's going to be 32 bytes. If it was on Apple, it would be 16 bytes. But it doesn't matter. It's a register of chars. Next thing I do is I do a load, right? So I load that much. And here I would load 32 chars. In my example, I show just 4 because I don't want to type 32 numbers. Step 3. We do the comparison. So I compare the loaded register against the needle. In SIMD libraries, it's very common. The comparison operator does not just return the bool. it returns instead a bunch of bools, like in a SIMD register as well. So in if, this is called if logical, right? And this is going to be like 32 bools conceptually. Okay? And for example, if my needle was 1, in this example, I'd get something like false, true, false, false. The next step is I'm calling this reduction function called first true, which returns me a position of the first true element in a logical. So in the example, it's going to be 1. If there was no true values, it returns an optional, so it would return you an unlocked. Finally, okay, so if there is no match, let's go to the next 32 bytes. And if there is a match, we found our result. Okay, this is pretty complicated. I'll give you a chance to have a look at it and ask me a question if you want to. Yeah?
What's the complexity of if first true?
It's 2 instructions.
So it does not perform a search, it's like a single instruction.
It is, yes, that's the whole idea of SIMD. All of this, like load, equal, first true is like 1 instruction. First true is mostly, well, maybe 2 instructions. I can show the assembly, but let's not. Like, oh, okay. Can I do this now? Yes. So, well, this is effectively first true, most of it. Like, this is what happens in a loop. This is computing the position. Like, it's nothing. Okay. Well, not nothing, but there's nothing interesting. Okay. Assuming everybody perfectly understood that, let's go. So this is the comparison. On the left here, I have... It's a big one. This is std find if. I used an if in there because then the compiler cannot do anything clever. I pass a predicate, and it has to, like, it doesn't do anything fancy. And this is what we would be writing in loop. The difference is 20 times. Okay. And now let's add std find to the mix, which calls memchr, and that is another 2x faster. What's going on? Well, the thing is, what's happening is unrolling. That std, what we wrote is not unrolled, and what they did is unroll. Let's have a look at unrolling. So this is our basic loop structure, like while first not equal last. You know? We can copy it twice. When we copy it twice, what do we save? We save 1 jump in the middle. There's the beginning. Well, we can also kind of do something like this. So we can merge the 2 iterations together, and then we'll have to handle something in the beginning, something in the end, that kind of stuff. And finally, maybe 2 iterations together can be processed faster than 1 iteration, one at a time. And this case actually falls specifically in the latter category. This is what we do. Let's take 4 registers, so 128 bytes, right? We compare all of them against the needle. Then we do an OR, another OR, and finally we just do an any. So we just, this is, right, substantially less instructions that do not depend on each other, then checking each one of them for a match. And if we look at the benchmark unrolled like that, this is what we'll see, that if std find is almost as fast as std find, I don't know why there's a difference. On Apple, stat find is just bad. They don't call memchr, but if beats std memchr by a factor of 2 because Apple doesn't unroll its standard libraries. That's the same reason we beat the previous implementation. I have no idea why they don't. Couple of notes on unrolling. So, the benefit of unrolling most of the time is doing less instructions. But as many of you know, your processor does a lot of instructions at a time, right? It's whatever, super parallel machines that does out of order, all that stuff. So when is it actually beneficial? This is kind of the simplest way to know. you take your benchmark and you run perf profiler with a stat command, perf stat. That's the first thing any performance person will do on a benchmark. They will run perf stat, and one of the numbers it will give you a number of instructions per cycle executed. My usual estimate is about 4 instructions per cycle your processor can do. It probably can do more, but that's kind of where I usually look at. If you have like 3 point something instructions per cycle, it means you've fully utilized the parallelism available on your one core machine. Right? In that case, you need less instructions. If you have like 1 instructions per cycle, it means that your processor can do much more stuff. Your problem happens that you cannot execute something because, I don't know, maybe you need to compute the previous value to compute the next value, some dependency like that. So this is how you know if you want to try unrolling, by running perfstat. Finally, if you go online and you Google unrolling, you will see the word Duff's device. If you don't know what Duff's device, it's fine. But if you do know what the word Duff's device is, I will tell you that I found it completely useless. Because the code gen that you want in the unrolled part doesn't match the code gen that you want in the tail part. I honestly tried. I didn't find it helpful. Any question on the unrolling? Yeah, there's a question.
So, I mean, I know what unrolling is, but I never had to do some kind of optimizations like that. Why is like unrolling an optimization due to the branch prediction we have? Like
branch prediction has nothing to do with it. You just do less instructions. Like like even if you just copy the code twice, that is minus a jump. That's already pretty good. That's minus a jump, right?
Ah, okay.
Like if you do just plus 1, right? You want to do 2 pluses in a row just to not have a jump around that plus. Here we just compare 2 registers. It's super cheap. Like you don't want maybe 2. An extra jump is 25% of the thing, right? You don't want to do that.
Yeah. Okay. Thanks.
All right. So finally, we're kind of ready for some people who are still with me to do search. The way we're going to do search is we're going to take find plus equal as our baseline. Kind of like that was pretty good, except also bad things. And we're going to improve on that. The more general version of a find plus equal is called Rabin-Karp algorithm. Well, you compute some hash of the needle, and then you go and compare that hash from like every character. In the case of find plus equal, your hash is just the first character. Wojciech-Müller, how many people read Wojciech-Müller blog? 0x80? You should read Wojciech-Müller blog if you like this stuff. So in his blog, he suggests to use first and last character. And that's what I went with because I really like that the first and last character is still applicable for 1 character needles, right? It still has, 1 character has still first and last character. That's not a problem. In Ash Vardanian library, Stringzilla, he uses 3 characters that he selects in some very clever way. And finally, str, as I kind of mentioned, uses first 2 characters, but it's not because they kind of had any thinking behind it, but because it is libc, it's C functions, it's really hard to get past the first or second character. Okay, so first and last character. Let's have a look at how kind of this works. So we have a haystack, we have a needle. So we're gonna have 2 pointers. The distance between them is needle length -1. The first characters will be comparing against the first characters, the last against the last characters. Let's load our registers from there, 32 bytes. And then compare the front character, well, the first against the first character, the last against the last character. So the only place where our needle can potentially be is where both the things are true at the same offset. So if they're both equal, this is where a match happens, right? So here's the intersection between this character and this character is the only potential match. And then we have to go through all the potential matches. And for example, here would be at this offset, like front plus whatever offset of this match is. Let's have a look at the code. Okay, so we have 2 pointers, as I mentioned, like front and back. And then we have the needle. So first we have, like, again, our register type. We load 32 like our register from front and back. And then we do the comparison. So front equals the first character, back equals the last character. This potential is this. So we computed this register here. Finally, then we have to go through all the potential matches. In find, we used first through. This no longer cuts it. So we have a different function called iterate selected. So you take a predicate, and you go through each match. And for each match, we just call memcmp to verify the needle. Okay. This is really complicated, but I suggest you have a look at it. If you don't manage to understand it, it's fine. Like, you're not going to suffer much. But if you do, that'd be cool. Any questions? Everybody understood everything. Yes.
Is there a reason why you return a Is there a reason why you return a boolean instead of like the position of the actual?
I store it in the front. It's a reference.
Perfect. Thank you.
So it's maybe a bit weird, but that's what I do. Okay. Let's just keep going. I showed you if code. So very few people actually use libraries like this. Most people, when they do SIMD, they use intrinsics directly or even write the assembly by hand. This is from the stringz library. And I'll just show you how the real kind of production SIMD code matches to what I just showed you. So, as I mentioned, stringz uses 3 characters. So this is loading free register. Load, load, load. This is this. Okay? Next, they do this ends. Right? This ends is this ends. So it's exactly this ends. So they compare against whatever. The first character is the last potential, the middle potential character, and the last potential character, and they do an end on them. And finally, they have this loop while matches do whatever. This is iterate selected. And this is called to mismatch, except they have their own whatever implementation of memcmp, except they all have their own memcmp. Okay. There are 2 potential improvements to this algorithm that we already kind of talked about. Who can try to guess them, if anybody can? Yeah?
You might want to use more than one thread for the comparison, or
The comment was I might want to use more than one thread. Sure, but that's done on top. Like this is a single core.
Maybe you could check more charters.
More characters. I could check more characters, but the problem is, so we pre-check 2 characters, so we can pre-check more characters. The problem is the more characters you pre-check, the less parallelism you have at once. There are, what optimization we talked about just now? Unrolling. We can unroll the pre-check. Right? And the second thing we can do is we can inline that memcmp. Right, because that's it's gonna check a lot of boundary conditions, and we don't want that. Oh, this was the unrolling scheme that we used for find, and I'm not wild about it for search. Can anybody guess why? It doesn't give the position. Yes, for a find, it is perfectly fine that we don't have the position of element we found because we just need to recheck once at the end. But for a search, we might encounter a lot of false positives. And so if we use an unrolling skinning like that, we increase the price of a false positive. Having said that, if you look at str, this is exactly what it does. This is about, and this is how we can inline the memcmp, the needle validation. Let's assume our needle is short. Then this is what we can do. We can populate a register with this needle and just remember to mask out everything past our needle. So that all of that is ignored. And then validation becomes super cheap. We just compare a character and compare the register and ignore everything that was masked out. If our needle is long, what we can do is we can take the first register and overlap it with the rest of the loop so that the rest of the needle is divisible by register size. What's really cool about this is that you can actually merge these two test cases if you just accept the mask inside the long needle validation. So just add extra masking here, and this is the same code. Yeah. So let's look at the numbers. This is str versus search that we just wrote for 1,000 bytes. For 1,000 bytes, Eve is a little bit slower. This is due to startup time. Not going to go into that. On Apple, str is just poorly implemented, so we just beat it. It's not interesting very much what was the results. For 10,000 bytes, Eve becomes twice as fast compared to str. So this is 10 times more elements. And the startup stops mattering, and we just beat str. It's very simple. str uses 16-byte registers. We use 32-byte registers. We just twice as big registers. I don't know why there's no implementation with 32-byte registers. Yeah, this is the false positives. So this is this is a real benchmark that triggers everybody's worst cases. So for str, they check the first two characters. So the worst case is 1, 1, 2 because the first two characters always match. For std search, doesn't matter. For us, it's 1, 2, 1 because the first and last character match, and so we call validation. And you can see that with our implementation on Intel, there is practically no overhead in the worst case scenario compared to scalar code. So that was really great. If we look on Apple, again, str is not interesting. There's not such a good result compared to std search for the worst case scenario, but it is, it is 2.5 times slower. It's not 10x or whatever find plus equal was. However, that's kind of benchmarking substring search, which is cool, but you should probably use a ready-to-go substring search. What about if you want to search something that is not just a substring, but some predicates? So this is benchmark if search versus std search for if search versus std search. So for chars, I'm going to say, well, it's less than 20 times. Let's say 16 times faster. For shorts, it's about 8 times faster. And for integers, it's about 4 times faster. So again, you can find a subsequence in a sequence on integers for 10,000 bytes, which is nothing, like 4 times faster than the standard search. Okay? Just plug in an algorithm. This is Mach, 3 times for integers, 4 times for shorts, and 10 times for chars. Okay. So huge thanks to Joël Falcou, who is the main author of the Eve library, Ilya Albrecht, who helped me optimize str and profile of the interesting things, and all the amazing people who share their results online. I kind of didn't have to invent, as you see, most of it. I just looked what other people do, which is cool. And different links. So you can find the library on Eve, GitHub, Joël Falcou, GitHub, Joël Falcou, Eve. The slides are again at tinyurl.com/dystr2025. If you want to see more SIMD algorithms, I gave a couple of talks. One is called My First SIMD. I recommend London C++ meetup version. I gave a talk called Advanced SIMD Algorithms and Pictures. I recommend Meeting C++ version. Me and Joel, we did a talk, SIMD in C++ 20. This is about the library at CPPCon. It's about the library itself, so how the library works. And finally, this year, I was almost 3 hours talking to people at C++ now about how to do SIMD ranges and what does it take, what does it's like very nitty-gritty details of if you're into that kind of stuff. And with this, I am open for questions.
Hi. Do you have the chance to have a look at C++ 26 support for SIMD, if you have some opinions about it?
Oh, I have some. I managed to, so I talked to Matthias Kretz quite a bit, who was one of the main authors, at least at some point. Matthias is absolutely an expert. He's an author of the VC library. He's absolutely an expert in SIMD. We have some disagreements, but generally speaking, it's okay. There's a main paper that was merged. It's okay. I have some problems with it. If you want more from SIMD wrappers, I complain a lot. There is some things coming down the pipeline that I'm not so wild about. The fundamental disagreements that we kind of have looks like this, that they believe if there is a useful operation that they can do on some platforms, they should give it to you. However, it might be that that operation that they gave you on your platform is really, really bad. Like really bad beyond the point that the scalar code is substantially faster, right? If you use a poor operation, and so what you end up needing to be me, you really need to know how all of that is implemented in order to make decisions whether or not you can use a library. And if that's not the case, to the extent that we possibly can, so it has some really awkward APIs, but the benefit of those really awkward APIs, they work really well across the board, including for people who don't know how to compile the correct code correctly. Yeah.
How is the Eve library different compared to the highway?
Okay, I have some opinions on the Google Highway. So Google Highway is, well, first of all, the Google folks always think that they are inventing the world, and so they, the main reason Google Highway exists is to support SVE dynamic extensions. Let me explain. I was saying here, oh, on my machine, this is 32-byte register, right? And I could use that even at compile time. I know that my register is 32 bytes. ARM folks came up with this idea. Like, I don't think this was them originally. There was some other people. RISC-V5 does some of the same things, where the architecture by default does not tell you the size of its SIMD registers. It says, so on ARM, it says between 16 bytes and 2 kilobytes. Like, I don't know what the 2 kilobyte register looked like, but and you're supposed to query at runtime the size of the register. Unfortunately, that leads to really interesting types in the C++ system, which have runtime size. So you cannot call size off on them. It's called sizeless types. It's an extension. It used to be that the GCC compiler had a support for that, and then we were trying to support this sizeless idiom. But then they removed it, and they only left specific built-ins. So Google Highway, because of this, Google Highway has a very specific design. It has a lot of passing things as variadics, and I didn't look that much, but my understanding, they have to pass things along as a raw a type, raw built-in types, and have some meta information on the side. And like, for example, very important thing for us is to implement zip. So you can take multiple arrays and zip them together into one kind of thing. And they cannot physically do it because this compiler doesn't support them. So this was their goal, and they really tried to make that work. That's their main advantage. The advantage of if it can do more stuff, it's much more ergonomic, but it will not support dynamic register sizes. So you have to build your code multiple times and link its DLLs or something. All right. From SIMD wrappers, I talk a lot about it.
Your turn.
My question is a lot simpler. It's why when you have like the 15 bytes data, you overlap the registers instead of adding a padding at the end of the last one, like you do for the small one?
Okay, I don't think I do. Let's have a look at that. So there's some confusion. So the reason why you can't load more is that because there might not be anything. It might be end of the page, and then you cannot load bytes where there's no bytes, right? But I don't add anything. So 16 bytes, we do 2 registers, one next to another. For 15 bytes, we overlap 1 byte. And for 7 bytes, we use smaller registers. It's different registers. You have to use 4-byte registers.
At the end, you showed a small data inside a bigger registry.
But the way that's done is a setup to make that work is either I'm using a specialized instruction that allows me to load part of the register, or I am copying the data to the stack in a bigger buffer and then load the register from stack. So there is some setups going on that happens once outside of the loop.
Okay.
So an algorithmic question. When you do your preliminary comparisons for the first and last characters of the substring in the string, for longer needles, does not make more sense to do 2 word comparison instead of 2 single char comparisons, like comparing the first 64 bits and then the last 64 bits of the needle in the string for a small overhead to have less false positives?
Okay, let me explain that. So you have when you have, let's say you just compare one character, so one character against, so you just want to pre-check just one character, so really poor hash. In one comparison of 32-byte register, you test 32 positions. Make sense? So in order to test 32 positions, you will need, for 2 characters, you need double as many instructions, double as many registers. All right? If you want to compare 8 bytes at a time, well, whatever way you do it, like it will reduce your parallelism for 8 times. So you'll be your no false positive case will be 8 times slower. If you compare, like, does that make sense?
Okay, so it's for like single thread parallelization of how the hardware works.
It is. You just take your big register, you test 32 bytes. However you want to test them, you will only be able to test 32 bytes in one instruction.
Yeah.
So if you want to test more bytes from each position, it will be less positions tested.
Yeah. So like when you test the front and the last characters, you are actually saying you are testing 32 bytes. 32
this
bits.
is 32. Yes, that's what we're doing. We take a SIMD register, and like look, here it is. This is one instruction.
Okay, so needle 0, it's a 32-bit
Needle
size.
0 is 1 byte.
Yeah, okay.
And you compare 32 bytes against 1 byte, each byte compared.
But it shouldn't make more sense to compare like even without SIMD registers, to compare like 4 bytes on a regular register, so you have less false positives?
If you have, I think, like, let's park that. Like, if anybody has a question, because I'm happy to talk more and show you more, but I think there's some misunderstanding here.
Okay, so maybe later in
Sure.
the coffee break.
Okay, catch me anytime. Yeah?
What happens if you had a case insensitive search on these algorithms?
So, ASCII?
They go really bad, or they can go quite the same as case sensitive?
I was talking about ASCII algorithm, because there's also, like, if you go to, I don't know, Unicode, that's going to be much worse and stuff. What encode? I was talking about ASCII.
Sorry?
What encoding are we talking about?
Maybe Unicode, maybe UTF-8.
So this is specifically for ASCII, right? This is bytes, effectively. If you want to do case-insensitive ASCII, there is a trick. It's going to be slower, obviously. There is an example in Eve. When it comes to Unicode, the algorithm is going to be really complicated. There exist SIMD-optimized UTF libraries. I had never worked with any of them. A lot of them, in one I saw in Chromium that just checked really quickly if it is ASCII everything. If yes, go happy pass. If no, do other things. Okay? That's it, I guess.